forgot to press the button, sorry very much. Okay, but you already take attention to my words, sorry, I forgot to start the record. Okay. If you have problem, of course, you can ask me the next lesson.
By the way, why the true frequency?
Yes, we are going to see. Because we can reduce for this error at first order. For instance, using a code observation, the pseudo range, we have the distance, the geometric distance corrected, that we are going to measure, corrected for the clock biases and for the ionosphere. We have for L1 and for L2. We can write two equations. If we combine these two equations in a linear combination, we can choose this coefficient N1 and N2 to reduce this effect. By this combination, choosing this special coefficient, the ratio between the frequency 1 power divided by the differences between the two frequencies and the other coefficient, you can see that in this case you have like a new observation called iono-free combination, and this iono-free combination you don't have this term. The term related to the coefficient, the ionospheric delay. So this is your homework exercise. So it's easy. It's just to say you can take this equation, you can put instead of this term the terms that we have seen before, C divided by power 2 of the frequency for the technical continent, and you can see that using this coefficient you can remove this term, the error. So, okay, when you observe you have a double frequency receiver, that means an antenna receiver that can collect the signal using the two frequencies. We can, in post-processing, when we take data and we put in our software at home in your office, you can use not just the equation for L1 and equation for L2, by combination, this linear combination. And this linear combination, the ionospheric effect is not present at first order. It means that when you have a very high intense solar activity, often this first approximation is not sufficient. And this is the reason, because now all this global navigation satellite system use more than two frequencies, at least third frequency, to reduce also for the second order effect of the ionosphere.
Sorry, at least how many frequencies?
3.
Okay.
And this is the iono-free combination. It's like you are using a wavelength. This combination corresponds to, we are speaking about phase, to 10 plus 7 centimeter. L1 means the phase related to L1. L2 means the phase related to L2. I simplify the notation, sorry. Okay. It depends. In this, sorry, just here I use the phase. Here I use the code. It's the same. We have seen that in the delay, in the ionospheric delay, the differences is just in a sign, minus or plus. Sorry, I use all together. But the ionospheric delay is present also. Is present in both observation, code and phase. We have just a different sign.
Okay, I going back to the the total electron content is?
It's a known quantity. We are going to see that we can use GPS to compute this for ionospheric study. So for us it's an error, and we don't know exactly this quantity. Okay, we can use other observation and have some model of tech, or you can use GPS to have information about this electronic content. We're supposed to fix our position and the position of the satellite, and we invert our formula, our equation, to term this quantity. This is done by colleagues that are studying the ionosphere. That is very important study for a lot of things, for communication, and also for other type of things. And so, because as we don't know this quantity, it's better to perform a iono-free combination, because in iono-free combination you don't have to know this quantity, because it's removed by the observation, by the equation at fourth order. Okay, so demonstrate that the iono-free observation L3 in phase on code you can choose is not affected by ionospheric disturb. It's just a simple computation that you introduce the term of ionospheric delay, and you estimate the parameter. Verify that with that parameter you don't have this type of disturb. There is another, this is not correct, I suppose, this link, because I remove was another video. Probably I have to check it, because I move, or not, I don't remember. Okay. Line, possibly agenda. Okay, just a moment that I'm looking for this video. I forgot to check. Okay, just a moment. Spotlight. No, it was correct, but probably something gone. Yes.
This video is about how to measure the atmospheric water vapor with the global navigation. But you may ask, why is water vapor important for us?
No.
Well, firstly, it helps us to predict
No,
weather,
this is
because
later.
it's the main source of water in the rain clouds.
This is water vapor. This one, sorry.
How to measure the ionospheric composition with the Global Navigation Satellite Systems, or GNSS. Most of you would say, but why do we need to know anything about the ionosphere? There are two very good reasons why we do. Firstly, because it's the medium where a long-distance radio communication takes place. And secondly, because it's very important for the navigation systems that rely on radio transmission. It all started in the beginning of the 20th century with the radio. In 1901, the Italian Guillermo Marconi initiated the first transatlantic radio transmission. Little did he know that this was only possible because of a yet unknown layer in the atmosphere. The scientists back then knew only basic things about the atmosphere. A close look at its structure shows that 99% of its mass is found in the bottom 30 kilometers, and above 1,000 kilometers we could not distinguish it from the interplanetary medium. The ionosphere is that part of the atmosphere where free electrons and ions are present in high concentrations. It is situated between 60 and 500 kilometers above the Earth's surface. But this This was unknown until 1925, when the height of the ionosphere was measured for the first time. Appleton and Burnett proved that the signal between the continents traveled not directly between the radio masts, but was reflected by the ionosphere like from a mirror. Let's see how the ions are formed, using as an example the nitrogen atom. Nitrogen is actually the most abundant gas in the atmosphere. Like all atoms, it has a nucleus and a cloud of electrons circling around it. The nucleus is positively charged, and the cloud of electrons is negatively charged. An electron can be split from the cloud by a collision with high-energy particles coming from the sun. This is why the ionosphere changes on a daily basis. During the night, when the sun is not present in the sky, there is only one mirror, the F layer of the ionosphere. With the sunrise, two more layers appear in the sky. These are the E and D layers. And all these layers, or mirrors, are different because they contain different concentration of free electrons and are situated at different altitudes. While the D layer is the lowest one, the F layer is the highest and contains maximum concentration of free electrons in the ionosphere. Now, the reflection or passing through an ionospheric layer of a radio signal depends on the layer's concentration and the frequency of the signal. At lower electron densities, the radio signal is permitted to pass, but when the electrons exceed a critical number, the layer starts to act as a barrier. The frequency dependence of the layer allows the building of the basic instrument for ionospheric research during the 20th century, called ionosonde. It works on the principle of sending successive pulses of radio waves from 2 to 20 MHz up into the ionosphere. These pulses are reflected at different layers, and their echoes are received and analyzed by the control center. For satellite communication, we need frequencies which will penetrate the ionosphere indifferent to its concentration. This is why Global Navigation Satellite Systems, or GNSS, use signals with 1,000 times higher frequency than ionosondes. But still, the ionosphere bends and disturbs the signals. These disturbances influence the position determination by reducing its precision up to several kilometers. And here is the clever bit. The GNSS, instead of using one frequency, uses two. Each of the frequencies is altered by the ionosphere on its way to the surface of the Earth. But if we find the difference between the signals when they arrive, we can estimate the state of the ionosphere above our receivers. This will provide us with not only better positioning, but also with data about the state of the ionosphere at any particular moment across the entire globe.
Okay. This one is a new one. I don't know. I don't know how to explain. I never see this video. At the end we can watch it, or you can watch it at home. Okay, it's important this video. We have seen two important things. We have found two important answers to your question. Yes. The first one was why. No, the other one. Yes. Okay. The first one was why the ray bending is higher in the low degree. The answer was that the 90% of the masses is in the troposphere layer. So when the signal comes from the highest layer of the atmosphere, it's not vacuum, but it's less dense of participle. And the other thing was about you see the yellow segments that say you have different refraction because we have different refraction indices. So in my formula was the integral, so n it's probably related to the layer. It's not a constant for all the atmosphere, but it's related to the layer, as we have said before. Okay. No, sorry. Okay, this is for the ionosphere. For the troposphere, so we have seen that in the, okay, I put 19% of the atmospheric mass in the tropospheric layer. We have seen that the tropospheric layer is a lower layer with respect to the Earth's surface of about 20 kilometers of altitude. We have 19% of atmospheric mass, but part of this mass is due to the water vapor present in this layer. Unfortunately, okay, during this the propagation of the electromagnetic wave in the troposphere, we have refraction and scattering phenomena due to the troposphere. The refractivity is due to the water vapor that it became like a dipole under the electromagnetic field of the wave. So, in theory, the magnitude of the delay due to the troposphere is less than the ionosphere delay. The ionosphere delay can arrive up to some meters, up to a meter at least. In this case, with the troposphere delay, we have an error of some decimeters, it's lower, but however, this delay is really important. It's more important than the ionospheric delay, because for the troposphere is not a dispersive medium for the GPS signal. So it means that even if we are using 2, 3, 4, 5, 6 frequency, we don't have any advantage because it's not a dispersive medium for the signal, and this is and we have two different contributions to the troposphere delay, and this we are going to see why we have problem with the troposphere. Okay, one contribute is due to the dry component molecular in hydrostatic equilibrium, and this molecular depend on the surface pressure and on the height. So we can model this component, but the very important component of the tropospheric error is the wet component, because the wet component is associated to the water vapor, and the water vapor is a very variable quantity in terms of space and time. Okay, we have is due to the affinity of the oxygen molecule, it became a dipole oscillating under the electromagnetic wave. Okay, and why the wet component is so important? Because we cannot predict which is this component, and it's changed really from one place to another place, and over time. It related to the weather, the weather forecasting. So how we can so in absolute term, the ionosphere error is bigger than the troposphere error, but the ionosphere error can be handled using the 2 or more frequency. For the troposphere, the wet component of the troposphere is very complicated to be modeled. So we can correct using observation coming from other instruments. For instance, radio sonde that measure pressure, temperature, relative humidity, and so on. Or water vapor radiometer, but are very expensive techniques. Now we have information from satellite and so on, but you cannot, it's not so easy. and we can model part of this error, especially for the dry component, if because the model are quite good to give you to model the dry component. Otherwise, we can estimate this error. So we are going to introduce new unknown parameters in our system, and we compute what is this delay for the GPS. So GPS becomes an atmospheric remote sensing technique. So as we have seen for the ionosphere, we can use GPS to have information on the water vapor present in the atmosphere, the troposphere, using GPS. We are going to see this part. So the tropospheric delay can be split in dry and wet delay, and each part can be modeled using a mapping function. For instance, the nil mapping function. Mapping function means that if you have a delay at the zenith position, this delay is propagated related to the elevation angle of the satellite. So it's sufficient to know the tropospheric delay at the zenith, and using a mapping function we propagate this delay at the different elevation. So you have a dry delay for at the zenith dry delay, and a wet dry delay, and a wet zenith delay, and you propagate this related to the elevation of the satellite. For instance, this is an example of a mapping function for a spherical symmetric atmosphere. That means that it's not related to the azimuth of the station. It's observations that coming from this direction or this direction in this type of model have the same delay. It's not related to the azimuth, to the direction, but just from depend just on the elevation of the satellite. And this is very simple. It's related to the inverse of the sin of the function of the elevation.
Okay, that's sin Z.
Sin, sorry. In Italy we use both the notation, or at least I. Okay. Now we try to use not spherical symmetric atmosphere. We start in the last 10 years or more, taking into account also for the azimuth direction of the signal, because it's different if the signal coming from the north, from the south, east, ovest. It's dependent. Probably in one direction there are mountains, so we expect a different water content or water vapor content, or so on. So it's approximate using a priori tropospheric delay plus zenith total delay, the total delay at the azimuth, and plus horizontal gradient that take into account for the different solution. So we introduce in our equation other unknown parameter, and we are going to estimate this parameter like our coordinate. The difference is if we have one day of data, we have just x, y, z for the geometric coordinate, and we have the problem of the ambiguity of the bias for the clock, but we also have this type of parameters. So for each satellite, not for each satellite. Just a moment, I have to remember. No, not for each. for every hour we are going to estimate these delay parameters. Usually the time interval is 1 hour, and not for each satellite. You introduce this in every... No, for each satellite, because we have signal for different solution. Don't remember, I have to check. It's a long time that I don't process GPS data. The last year I have to check a report. Don't remember. You introduce this parameter in each observation, of course, and you are going to estimate. Now, for each station, you have a set. No, okay. For each station, you have a set of tropospheric parameter in terms of delay at the zenith direction, in terms of gradient. Take into account for this not symmetric condition. So the number of unknown parameters is really increased, but it's not a problem because if you, the receiver tracks the satellite, we collect observation of a given at a given rate. For instance, we collect data every 30 seconds, every 10 seconds, and so on. Now we use receivers that can perform measure with 1 Hz of frequency, or also bigger 20, 15 Hz of frequency. So the number of the observations that we have at the end of a daily observation after 24 hours of observation is really big. So we can introduce other parameters without ever any problem in our estimation. And this way we improve our estimate. All this type of estimation is made by what we are going to see by the scientific purchasing software. We are going to see that we can use different type of software to process GPS data and to deal in a good way. At troposphere we need a scientific software able to estimate the zenith total delay, but also the gradient. And okay, this was about the cutoff angle. Now we try to use all this information because to estimate also the gradient we need observation also from very low satellite with respect to the horizontal. So usually in the observation we put cutoff angle equal to 0. In the processing step we use about 5 degrees. In the past was really high with this cutoff angle, so we cancel out of observation. So GPS can be used also for meteorological application. For instance, in the department, you are in ICTP, you know, you are studying solid Earth, and your colleague atmosphere and ocean science. And today we're walking around the office. I look at a poster by the other colleague for the atmosphere group that speak about the estimate of the troposphere parameter by GNSS technique. So they use this part for us is an error, a source of error for your colleague is the observation to take information about the total water delay. So we can estimate this part, we can remove the hydrostatic component using model, so you can estimate the wet delayed, and you can compute from this quantity the integrate principal water vapor, so the quantities that can be translated in rain, in snow, and so on. And there is also other video on this part that they use GPS for meteorology. And this is also important for we are going to see that we can use GPS for InSAR measure to correct the InSAR measure for the tropospheric effect. So all the techniques are related. And now there are, at least in Europe and I suppose in the United States, I don't know, in the rest of the world, a lot of GPS are used for this type of application to give a model of the water vapor, integrated precipitable water vapor. So I will show you also this video. In the afternoon we need a video. Okay, again, but where okay, I can. No. Ok, ce l'ho già preso. Ok. Ok.
Secondly, it's the most abundant
I
greenhouse
start
gas
again.
accounting for 70% of atmospheric warming today. This video is about how to measure the atmospheric water vapor with the global navigation satellite systems. But you may ask, why is water vapor important for us? Well, firstly, it helps us to predict the weather, because it's the main source of water in the rain clouds. Secondly, it's the most abundant greenhouse gas, accounting for 70% of atmospheric warming effect. Let's take a minute to have a look at the Earth's atmosphere. Imagine this is our planet, the Earth. As you may know, the Earth's radius is about 6,400 kilometers. The Earth's atmosphere is a thin shell of air which goes up to 1,000 kilometers. Let's now have a close look at its vertical structure. Do you know that some 90% of all mass in the atmosphere is found in the bottom 15 kilometers? The lower 30 kilometers contain 99% of the mass of the atmosphere. And above 1,000 kilometers, we could not distinguish it from the interplanetary medium. But we are interested in the bottom 15 kilometers, where the atmospheric water vapor is found. This layer is known as the troposphere. Tropos is a Greek word meaning turning and mixing. And indeed, the vertical mixing in the troposphere is such that if we take a drop of seawater, it can eventually evaporate and become a flock of water vapor molecules, which can rise and condense and form a cloud. And then water can fall back to the surface like rain. And all this will happen within a week to 10 days. Indeed, 85% of water in the atmosphere is evaporated from the oceans, with the remaining 15% evaporated from the land. Interestingly, over 90% of water vapor is found in the lower 5 kilometers of the troposphere. How do we know, you may ask? Well, easy again, we can measure it. By putting a sensor on the balloon and let it fly off, we can measure the amount of water vapor on its way up. Easy, isn't it? This method is known as radio sounding. For many years, this was the only way to measure water vapor in the troposphere. But this was changed with the development of the Global Navigation Satellite Systems, or GNSS. One of them is the Global Positioning System, or shortly GPS. The widely known application of GPS is position determination, with extremely high accuracy, better than 1 centimeter. Since early 90s, scientists have come up with yet another use of GPS, namely to measure the atmospheric content between the satellite and the Earth. Now, do you know how GNSS works? Well, let's take a minute to explain it. A system of man-made satellites, very far from us, send a signal that travels with the speed of light, reaches the Earth's surface in about 10 milliseconds. 10 milliseconds are actually 1/100th of a second. But on its way, it passes the dense layers of the atmosphere, and the speed is reduced a little. First is the dry atmosphere, a mixture of 78% of nitrogen and 21% of oxygen, which slows down the GPS signal, causing a time delay of 1 to 2 nanoseconds. Versus meters, we can predict with high high accuracy that it will have about 2 meters to the satellite receiver distance, which varies with up to 1% in a few hours. However, the actual measured distance is different, where it does
It's lower and lower.
the atmosphere has this
Volume.
dry air, but also water vapor. And importantly, water vapor has a very high temperature variability, changing from day to day, from morning to afternoon, from hour to hour, adding between 1 to 80 centimeters to the satellite receiver distance. So this is how you can measure water vapor using the local navigation satellite systems.
Okay, sorry for the volume was really low. Okay. Okay. Okay, in the modeling error, we have seen that clock bias, orbit bias, and atmospheric biases are the most important. For the phase measurement, we have also to take into account for the ambiguity and for the phase center variation. I think that we don't have enough time to see this, to start to see this problem. So. I think that for today we can stop here. I can spend some word about the exam.